Hello, class. Welcome back to numerical methods. Today we're going to turn away from fitting lines in general with lots of data points and start considering cases where we have relatively few data points, where we need to do interpolation rather than fitting. Where this is coming from is last time we've talked about things like polynomial regression, multiple regression, general least squares models, where we have lots of data and we're trying to fit a simple or complex model with lots of data, where we can use that sum of squares based approach, where we take a fit and then we assume some sort of solution, and then we minimize the error in some variables of the model to the data. However, what we're going to talk about today is a case where we have relatively little data. What this means is we can no longer do fitting, and we now have to go towards interpolation. Within this, we're going to talk about polynomial interpolation, specifically within the Newtonian and the Lagrange polynomials, how this can be applied to inverse interpolation problems, and then we'll talk about the dangers of doing interpolation and extrapolation and how this can lead to oscillation. But first, let's talk about the need for interpolation. A lot of times data is relatively sparse or highly nonlinear in an area of interest. This means we can't get enough data to really fit a line or a curve to as well as we might like. So you might say, well, can't you just go and get more data to provide a better fit? Well, maybe. Sometimes collection of data is highly expensive. So you could think of having to buy a standard, and those standards can be hundreds, thousands, or even tens of thousands of dollars. So you may not want to do 5 data collection points if each data collection point costs $10,000. Conversely, if you're thinking about a drug trial or some sort of pharmaceutical approach, this may be even more than $10,000 and require months or even years of data. So we can't always just go out and get more data. Therefore, we need to take the data as it is. So if, say, we have 2 data points, the best way to say is, if we only have 2 data points, the best thing that we can say then is just whatever's happening is on a straight line between these 2 points. If we have, say, 3 points, we can see immediately that just fitting a best fit line, which would go like somewhere through there, or even better yet, something like that, is not going to represent, say, all of these data. We have to assume, when we have such little data, that each of these points is accurately representing what's going on at that spot. So we have to maybe fit a parabola that would then more accurately represent the shape of that data. And we can do this not only with lines and parabolas, but we could fit maybe a cube, so we can take into account more of this data. So we can do these polynomial interpolations where we fit a polynomial, and then we can go to any of these x's and read off their y values up to 2 degrees, up to the number of points we have. So let's say we could consider this with 2 points up to a line. 3 points we can do quadratic, and 3 points cube version. Let's go in and see how this might play out in some data sets. So here we could be asked to fit a relationship between the temperature of a fluid and its density. If we just fit a straight line, which we can see here, we can actually get a pretty good coefficient of regression, so that R squared value. However, we don't necessarily know how good this point is. We can see that there's some sort of curve possibly, but we don't know if that's real or a line. Let's just say, for example, that if we were able to take 2 more data points, say shown in orange, they would sit here. This would indicate that our line fit would overestimate the density at any given temperature. So we would have a relatively poorly converged set. What we would want to do then is to fit these 3 points in blue into a parabola. If I just sort of draw out what this would be roughly, this is much gonna fit those orange points much better. So what we can do is take the data points that we have and fit them using our polynomial formula, and we'll get exactly a line that will go through each of those 3 points if I were to put in a cubic version of this case. So if I do that, and remember what we want to do is we want to put this into a linear algebraic form, where I have my x's, my coefficients, and then my values. Shown down here is that generic form of a fit. Remember, from last time, we can use linear algebra. We just have to change the variables. So in this case, if we're doing a quadratic fit, we would end up with x squared of data point 1 x of data point 1 and 1. And then same thing, x squared of data point 2, x2, 1, x squared of data point 3, x3, and 1. And then the coefficients, say P1 for polynomial coefficient 1, 2, and 3 of our system. Then we could go in and take out the experimentally determined y values to fit. In this case, I have a linear equation. 3 equations, 1, 2, 3, 3 unknowns, P1, P2, P3. This is going to perfectly fit. What you'll notice, if we look at this matrix, is we have a squared term to the first power and to the 0th power. So I could put a 1, and this is then that 0 power. This is called a van der Mode set of linear equations, a van der Mode matrix. This is going to give us a very ill-conditioned matrix, right? Even though it will give us the desired result of P1 x squared plus P2 x plus P3 equals our f of x, right? So that's what we want. But the issue is this is very ill-conditioned, because now all of a sudden I have these squared terms in relationships to these to 1, right? So this squared term can get gigantic if x is a big number, or it can get tiny if x is a very small number, right? So this means this difference in exponent can lead to large errors, very ill-conditioned matrices, and therefore large errors just associated with the numeric methods. So let's sort of see how this ill conditioning might set up. Right? So we can take these 3 blue points again. We can say that they occur at if they occur at 300, 400, and 500. So this is our temperature, and this is our density. We can plug them into this equation to form our matrix. So here we take 300 squared, 400 squared, 500 squared. which are 90,000, 160,000, 250,000 as the first column, 300, 400, 500 is the second column, and ones all the way down to the third column. Then pulling off our densities over here, we can just plot them in from that density table. Once this is made, it's relatively easy to now go and plug this into Matlab. I'm not going to type this all out, but we can sort of, I've pulled the answers out of Matlab. So just for the sake of making sure that we can see all the digits, I've put in this format long case and then typed in our A matrix based on the previous slide, the B matrix based on those densities, and then using back division, we can get our P's. So if you do all this out, you get that P1, which is our x squared term, to be 0.000000115. And then we get our associated x term and then our x to the 0th power term. So those 3 points are associated exactly with this parabola defined by this equation. So 0.0000115 x squared minus 0.001715 plus 1.72. So this is the good news. It's relatively easy to do this. And we can check and see what our f of x value might be, or the density might be at a temperature of 350 degrees C. All I need to do is take that 350, plug it in there, and we can find out that our density might be 0.567625. So relatively easy to do this. But there's a little bit of bad news. The conditioning on this matrix is very poor. If I type in the condition of A, my answer comes out to be 5.8 times 10 to the 6th. This number is huge compared to 1. Remember that 1 condition number around 1 is going to represent a well-conditioned matrix. We are very far from 1. Also remember that the number of digits that we trust is proportional to the log of the condition matrix of A. In this case, this is going to be approximately 6. This means we do not trust, we only trust the first 6 digits. Well, let's go in and look at this. I have 1, 2, 3, 4, 5, 6 digits here. Oops, sorry. Miscounted one. 1, 2, 3, 4, 5, 6. This means I trust these first 6 digits are zeros. I'm not sure that that first digit is a 1. This means that I really don't trust that first one, not due to any sort of philosophical reason, but just due to the accuracy of inverting these matrices to perform Gaussian elimination. Okay, so we can start seeing where the problem might come from using this format. Instead, we're going to try to use different interpolation forms. But before we do, I want to quickly go in and remind ourselves how we can use inbuilt functions polyfit within Matlab to get the same answer without having to do all these steps piece by piece. So once again, this is still going to be doing that traditional way of fitting a line using Matlab. Instead of using back division, here we're going to use polyfit and polyval. So remember, we can use that format long. If I input some temperatures and densities into Matlab, I can then use this polyfit function. Remember, for polyfit, I put in x, y, and the order parameter that I'm interested in looking at. Previously, we had put in more than enough data. So if we had, in this case, if we were looking at this squared term, we would have many more points than just 3. If I only put in 3, polyfit is going to do exactly what we did on the previous slide, but sort of all wrapped into one, where it's going to perfectly fit a line that goes through all the different points. If we do this, we get our p coefficients, which pop out of here, that exactly match what we saw previously. We could then, if we wanted to, use the polyval function in order to go with the polyval function in order to with that calculated p, and then this is the t that we're interested in, and it would pop out that d term which we calculated on the previous slide. So same thing here. We're still going to have suspicion about these digits in that 6th digit spot. So with this in mind, we can start seeing where we might want to move away from fitting overfitting these lines and move into some sort of interpolation scheme. Let's first look at Newton's interpolating polynomials. Let's say that this this blue line on this graph is the true data points, but we don't know what that true line looks like. We only know this black point here and the black point there. Even if we wanted to, we don't have enough information to fit that blue line. We only know what's happening at these two endpoints. So the best we can do is a linear fit. So let's say we're interested in finding a value at x, which lies between x1 and x2. I'm just calling it x so that we can make it be generic. What we can do is we can use similar triangles by noticing that this triangle and this outer triangle are similar triangles. This means that the ratios between the slopes have to be the same. So we can look at the slope here and compare that to the slope here. So let's put some numbers on here. So we can say that f of x1 minus f of x2, right? So the slope, maybe I'll keep that one in red. So the slope over the whole thing, so over x1 minus x2, must be equal to the slope over the small triangle, or that piece that's in purple. So that would be f of x, okay, so this point, minus f of x1 over the distance between x1, or x and x1, right? Just so that we have the similar slope. So from this, I can rearrange this formula to get this piece, pick a different color. I can rearrange this formula to get this f of x, which is what I'm interested in, all alone, right? I can move this term over by multiplying and then add this to the other side. This is going to give us Newton's interpolation formula. So when I do this, I get f of x equals what used to be on the left-hand side. So f of x1 minus f of x2 over x1 minus x2 times what was on the bottom, so x minus x1 plus f of x1. Right? So this is our Newton's interpolation formula. We can take a similar idea and extrapolate it further outwards if we knew one additional point. So let's once again say that this black line, which in this case, or this example, is set to f of x equals the natural log of x, is our true solution to the natural log of x. And let's say we knew 3 points in general, so shown here, and we wanted to interpolate based on this information here. If I know only 1 point, I would get this dashed line. But we know a little bit more information because we have this 3 points to use. I can extrapolate out the Newton's interpolation formula to this equation. So I still get to maintain those first 2 terms. Oops. I still get to maintain these first 2 terms from the previous slide for a single value. And then I add on essentially a correction term. Right? That's going to move us away from this linear piece into this quadratic piece. I'm not going to go through the derivation, but we can go through each of these individual pieces. We can write this more compactly by looking at each of these terms. So here we have this f of x, which has no dependence on x, so I can put this all out by itself in this term b. If I then look at this, at the second term, I see that I have a piece which depends on x, right? So our dependent variable, and a piece that does not depend on x. So this piece that does not depend on x, I'm going to call b. In this case, it's b2 because I already had that b1. And then we have to keep this secondary term which depends on x, and that lives right there next to b2. Then we can conquer the quadratic term. Once again, if I look through this when I look through this equation, I have a piece on the left which has no dependence on x. It definitely depends on x3, x2, x1, but those are known fixed points that are coming in from some data set. It's only the pieces on the right of that line, that right part of the term, which have x dependencies. So this first part we're once again going to call b, in this case b3, and then we need to keep these terms that depend on x. So I can put out here that f of x is b1 plus b2 times x minus x1 plus b3 times x1 minus x minus x1 times x minus x2. You'll notice that I've included an extra 2 in this f of x. That 2 is going to indicate that we're doing a quadratic fit. If I was doing a linear fit, this would be, that 2 would be a 1. If I was doing a cubic fit, it would be a 3, etc. Okay, so let's look a little bit more at those individual b's. I've written out already what those b's are down here, basically from copying down from that top equation. Our b1 is just the f of x. b2 is the slope between the slope between points 1 and points 2. b3 is really the second derivative of these different points. So that second derivative, which is going to give us a curvature, is represented in b3. You'll also notice that b2 is represented in b3, right? This second term right here is b2, right? Both of them have f of x2 minus x1 over x2 minus x1. So this term is b2. We can notice sort of the same thing up here in the second, in b2, right? That second term is equal to b1. So we're going to see this cascading effect. I also want to point out that when I look at these terms, I have going from left to right on b3, I have f of x3 minus x2 over x3 minus x2. So we have matching x's. In the second term, I have x2, f of x2, and f of x1, terms which are once again matching. And I do the subtraction. You'll then notice that x3 and x3 match, x1 and x1 match. And you'll notice that as I move across the top, I go 3, 2, 2, 1. So these inside terms are going to match. Okay, so we can start to see a pattern. And this pattern is going to exist for any higher number of terms that we want to include in our interpolation. So in general, the n-1th polynomial interpolation has all of the terms of the n-2th polynomial plus one extra. In other words, if I'm adding on this last term for this n, I get to keep everything to the right, or sorry, everything to the left. All those terms that have already existed, I get to keep. This makes adding an additional term or an additional piece of data relatively easy because I don't have to get rid of any of my data points. If I add one extra data point, I want to increase the degree of my interpolation, I can do that without changing my previous results. In each of these cases, our b's, which we had set is some function of x's, and we saw in the previous slide, are actually divided differences, right? I take my f of xi minus f of xi minus 1 and put that over xi minus xi minus 1, right? I'm taking divisions of these differences. And as I build up each additional term, I add one more divided difference. So this is going to, this pattern of taking divided differences is going to make life a little bit easier. So in practice, what we want to do is start making these tables. Right? So here's an nth order set of divided differences. If I have only two terms, I take f of xi minus f of xj over the difference. When I add in the third term, I use my divided differences from above of the two individual points. And then I keep having those sort of waterfall down. As each of my divided differences grows, I have fewer terms. So let's say I had 4 data points. If I had 4 data points and 4 f of xi's, right? This means I can get at most 3 terms. I could fit a cube. For my first divided difference, I look at points 1 and 2 to get f of x1 and f of x2. Then for the next set of differences, I take x2 and x3 to get f of x2, 3. And then finally, I take the last pair, x3, x4, to get f of x4, x3. I'm only ever going to use this top term for my first divided differences, but I need two terms, these first two terms of, I need two terms from the first divided differences in order to get my second difference, right? So I need f of x2 and x1 and f of x3 and 2 to get f of x3, x2, x1. And then I need the last two to get f of x 4, 3, and 2. The reason why I need this f of x 4, 3, 2 is because if I want to go one more term out, I need two terms to do a divided difference, and I get my final third term. Right? So I can create these tables and continue to take divided difference after divided difference. So I'm going over, going over, going over until I've run out of terms. I can't go to a fourth, right? There's no way to divide another difference. I want to point out that in these divided difference terms, we always have the this highest order, this n term, sitting here, and one sits at the far right-hand side. I have 2 sitting, x2 sitting as the last term of the first f of x set, and n minus 1 as the first term of that second divided difference. And then I get my xn and my x1 in the denominator. Let's do an example. Let's consider that we're looking to calculate the natural log of 2 using third order Newtonian interpolation. Given the fact that at x equals 1, 4, 6, and 5, the natural log of x equals 0, 1.38, 1.79, and 1.60. I will denote to you that we don't necessarily have to go in order, right? I can go 1, 4, 6, 5. I don't have to have these lined up 1, 4, 5, 6. This is important because I can always go back and add data, and that data doesn't have to lie on the outside. It can be between two existing data points without messing up our method. So here I've written out the third order Newtonian interpolation formula. Here we have our b coefficients, and we have the x minus 1 term, and of course every b gets one additional x minus unknown data point term. So let's do first things first. b1 is easy because that just equals f of x 1. So whatever that first point is goes in there. In this case, x1 is 1, and so the natural log of that first term is 0, b1 is 0. That's a nice freebie. Now we need to do our first order divided differences. So here we can say our, gotta give myself a little more space. b2 is going to be f of x to x1, which is the f of x's subtracted from each other, so 1.386294 minus f of x1, okay, that's 0, over the difference between the values, so that's 4 minus 1. When I do this out, I get 0.462091. I can then do the rest of these. They're not going to equate to any b's, but I'm going to need the higher order f of x's, first order f of x's, in order to calculate further divided differences. So my f of x3 and x2 is just 1.791759 minus 1.386294 over 6 minus 4. This is going to be equal to 0.2027326. And then my fx4, x3 term is my last data point, 1.609438 minus 1.791759 over the difference between my 2 points. That's 5 minus 6. This gives me 0.1823216. So once again, we're only using directly B1 and B2, but these latter two f of x's are going to be needed to solve for B3 and eventually B4. So let's go ahead and do that. Here I've written out the formulas for the third order term. Oops. For the third order term. So we can go in now and solve for it. So my f of x3, x2, x1 is equal to 0.2027326 minus 0.462091. So those are those f of x's from the previous slide. Now I need to take the next two set of x's. So 6 minus 1, that's negative 0.05187311. And I can do the same thing with my x4, x3, x2. In this case, the second order x4, x3 had a value of 0.1823216. My x3, x2 first order term was 0.2027326. All over my x4 minus x2, so this one was 5, this had a value of 4. So 5 minus 4, this is going to give us negative 0.020411. Once again, we're only going to use this term for x3. This is our B3. This secondary term, that second 3-term f, we don't need. We don't use directly. Instead, it's necessary to get that last divided difference, that, in other words, B4, that gives us x4, x3, x2, x1, which is the divided difference between the two. So negative 0.020411 minus negative 0.05187311 over x4 had a value of 5, x1 had a value of 1, 5 minus 1. This gives me a value of 0.008665529, and this is our B4 term. So I can take all of this information and put it into a nice table. In the end, as you're working through these problems, I highly recommend that you build this table. This then is much easier to take each of these divided difference terms and build them up. You'll know that you've completed it because you'll end up with a term that you can no longer do divided differences with. So we can take these divided difference terms, we can write out an equation, say f3 equals 0 plus 0.46209881. Remember, we're essentially going to take only that top line, except I've now drawn over it. We're going to take exactly that top line. We're going to write out minus each term. So x minus x1 was 1. I now pull that second term, minus 0.0518731. I maintain that x minus 1. Now I put x minus x2. X minus x2, x2 was negative 4. I then pull in my third term, which I'm going to have to go down here, plus 0.007865529. And then I repeat all of those terms, x minus 1, x minus 4, x minus x3, in this case, was 6. Right? So this gives us now an equation, our Newtonian equation, our Newtonian interpolation equation. We can check to see how we did. So we can take the natural log of 2. This is going to be 0.693147. And we can actually calculate out our f of our Newtonian interpolation. I'm not going to write out all of the math, but if I plugged 2 into these x's up here, we would get 0.628766, which gives me a true error of 9.3%. So not so bad, and not so bad of an error. And while it's very tedious, right, to go through each of these iterations and calculate each divided difference, is very computationally tractable. So let's sort of look and see what happens here. That black line, once again, is our true value for f of x. We can see in the blue line the estimate using our Newtonian interpolation. What you'll see is we get quite close to our true value. That blue line gets even closer to the value, to the true values, when the distance between our data points is relatively small, right? So the distance between our x1 point and our x2 point is big, and that's where we see the biggest error. As long as we stay within this interpolation regime, right? So as long as we stay between the data points, we're relatively good. I want to point out to you that as soon as I go outside of this last data point, we extrapolate. In this case, we see divergence from the true solution. This may not always be the case, but we should always be very wary that whatever happens outside of the data set that we're trying to fit, because we don't know if it's going to diverge from the true solution or maintain a good fit. Now that we've covered Newtonian interpolation, I want to cover Lagrangian interpolation, or Lagrange interpolating polynomials. The idea behind Lagrange interpolating polynomials is the idea that if I have a point here and I have a point here, any value between them should be a certain percentage of the total value, right? So I should have something, my f of x should be some fraction of f of x1 plus some fraction f of x2. Because Lagrange invented them, we use L's for Lagrange. So when you go out there and you invent some cool new math thing, you can call the variables after your own last name, give them that format. So the question becomes, within here, we know that we need some sort of portion of that fx1 value, we need some portion of the fx2 value, and what should those be? Well, we also know that when x equals x1, f of x should be equal to f of x1. And similarly, when x equals x2, f of x should be equal to f of x2. And they should be somehow proportional to this idea. And when we're in between there, it should be proportional. So the way that we can make this work is by setting L1 such that it's x minus x2 over x1 minus x2. When I do this, if x equals x1, this whole term, this L1 term, becomes a 1, right? So that would then satisfy that first constraint as long as our L2 term would go to 0, right? So what could we do there? Well, we can put it sort of the other way. We can say L2 would be x1 minus, would be x minus x1 over x2 minus x1. In this case, I'm still premising our idea on what happens when x equals x1. L1 would be x1 minus x2 over x1 minus x2 is 1, and L2 would be x1 minus x1 over x2 minus x1, 0. So this mathematically is going to work for that when x equals x1. I can try again, maybe in a slightly different color. We can check to see what's going to happen when x equals x2. I get x2 minus x2 over x1 minus x2. Oh, that's 0. And then my L2 term becomes x2 minus x1 over x2 minus x1 also equals, and this time equals 1. So we satisfied that secondary term. Right? So this format is going to allow us to interpolate these two different values. So previously, we had sort of taken sums of differences. Now we're going to have each of our terms coming out as these, we're going to hold constant, or a set of these f of x terms, so these the y points as constants, and we're going to change these fractions out in front. Let's generalize this to a larger number. In this case, we can say that any interpolation value at f of xi is going to be the sum of all those L terms times f of x I, where these, any f of x interpolation is going to be the sum over these L proportion terms times those data point values at I, where L2, Li is going to be the product given by this pi sign for j equals 1 and j not equal to I to the nth degree, so however many data points we are coming out to, of x minus xj over xi minus xj. Okay, So building this out, we could say f to the first power is going to be L1 times f of x1 plus L2 times f of x2. Okay, so we've written out that first part of the equation. Now we need our L1. So in this case, we take our product terms. We only have one value, so we only have to do this once. So we have x minus j, so where j is not equal to I is 1, so it can't be 1, it has to be 2, x2 over, oops, this is supposed to be j, over the I term that I'm looking at. So this 1 goes here, so x1 minus x2. And we can do the same thing for L2. This is x minus j, where j is not equal to I, so it has to be x1 over xi. This is, the I is 2, so that's x2 minus xj, which is x1 again. Okay, we can put this all together. We'll get the exact same equation that we had on the previous slide. Oops. Okay, well, x1 minus x2 f of x1 plus x minus x1 over x2 minus x1 times f of x2. Okay. We're going to come back to the Lagrangian interpolation later in the class, but now you have an idea of what this is going to look like. Now that we've talked about the major methods of interpolation, I want to touch on some of the dangers of interpolation. First, inverse interpolation. Often we get some sort of data set where we take some sort of dependent variable, say, for example, the concentration of a certain molecule in solution, and we measure some response, say it's absorbance, right? With the idea that we could fit some sort of curve to this data, and then try to get back, measure some unknown samples fluorescence, and get back f of x. Right, so we measure using the dependent variable, and then we get out, we measure against a independent variable to get a dependent variable. And then we go in and we essentially measure the other way. The issue, the first option to say go backwards would be to flip the x and the y. So plot the x that we're looking for against this f of x that we sort of have. So can we just take this x, put it here, take that f of x, put it on the x-axis, and then fit a curve, interpolate some sort of curve? Well, the problem is that this can lead to oscillations. As you can see here, while the data should be some sort of monotonic function, we get this oscillation down here where the data is sparse. The data may not have been sparse in x, right? Each of these x points may be the same distance apart from one another. But now the distance between their y's is the distance between the x's down here. Remember from our previous discussion that the longer the distance is between the x's, or what we're using to fit as the x's, in this case f of x, the less accurate that we're going to get. In particular, where we start getting sparse data, we end up with these curved oscillations. So the solution to this is a root finding method. We can fit the function up here with the correct dependent variable, which is nice and evenly spaced, against the f of x value. And then we can use one of our root finding methods to take the value that we're looking for. So say, once again, some sort of absorbance minus the f of x of the fit, and set that equal to 0, and ask the computer to find the x that makes this equation true. By doing so, we get to use the nice evenly spaced data in x, as opposed to having this unevenly spaced data. I further want to touch on hazards when we talk about extrapolation. Remember that interpolation is when I have points and I'm looking for data between these known data points. Extrapolation is what happens outside of the data, right? Outside of the data range. Let's say I fit this, if the black is our true curve, and we have this blue line as the fit between these 2 points, if I move to the right of x3, I can end up getting an answer that sits down here, as opposed to the true answer, which would sit up here. And this can get worse. We don't know what's happening outside of that extrapolated region. All we know is for sure is what's happening inside that region. So we should be very wary about any sort of extrapolation. Let's see what this might look like if we, using the first 8 decades of US population in the 1920 all the way through to 2000. Here, I can have the dates of the different population, and then I can put in the associated population values. So here in Matlab, that would be 1920:10:1990, and then I could put in the associated population. I could then use that polyfit function like we did previously. When I do so, I'm going to get this number, this warning popping up that says the polynomial is badly conditioned. Remember, if I'm trying to fit this data with an order 7th term, I have my first matrix, which is x to the 7th, x to the 6th, x to the 5th, x 4 to the 3rd power, squared, 1, and 1. When I take 2000 and I put it into x to the 7th, and I compare that to the value of x to the 1, to 1, it's huge. It's no wonder that I'm going to have a very poorly conditioned matrix. When this happens, we have to do some data shifting and data handling so that we can make sure that these data sort of fit a little bit better and aren't so far apart. How we can do this is called shifting the data and scaling the data. Shifting the data is we subtract some points, some numbers off the data so that the center is at 0. The idea behind this is the highest number should not be then too far from 0. We could do that, say, by having some time shifted variable that's the time, so say the year, for example, minus the average of that value of the set. So if you remember, we went from 1920 to 2000. Our median value would be 1955. This is going to then shift the data. We may also want to scale the data. By scaling the data, we're going to divide by some number, or in fact multiply some number, so that the highest value is 1. So remember, if this is 2000 minus 1955, that largest value comes out to be 45. So by dividing by 35, this gets close to 1. So we should have less problems. So we both shifted the data, so taking the center to 0, and scaling data so that we have a smaller range. Now if I go in and I use polyfit again, I will not get, we'll get the result that we want. So here we can use polyfit to get our p-values, so those different coefficients. We don't get a warning. I can now use polyval, which will take any of those, any input number and use those p's to return our value. We still have to remember that when we use this to do the associated shift and the associated shift and the scaling. If I do this with 2000, I get 17 175, which is close to the true value. And we can take this and plot that on these different curves. So here we have the data points, and then in black showing our fit. What you'll notice is with this high order polynomial, we get very fine and close definitions as long as we're interpolating. However, what this graph would say is after the year 1990, we're going to fall off a cliff, right? So this would predict using a 7th order polynomial that the US population would decrease dramatically in the year 2000. Unfortunately, or I guess fortunately for those of us living in the United States, that didn't happen. It continued to go up. So this is both an example of how we can do shifting and scaling, and then the dangers of extrapolation. As we see in this, values, we end up having oscillations with the higher order of the polynomial. So let's take 2 more examples. So if I look at the example on the left, when I fit using these points here, and I only fit using, say, a 4th order polynomial, I'm sorry, a 3rd order polynomial, we can get this nice, much smoother curve. If I go too high and use a 4th order polynomial, I can end up getting these wide oscillations. And these wide oscillations tend to occur due to overfitting of the data, right? That line is perfectly going to hit each of those points, even though that may not be what's really happening. Not only do we have these oscillations, which is called Runge's phenomena, but they tend to be centered on the outside of the data. So if I go to an even bigger data set with more data points, we can see that that the oscillations lie on the outside, while we can have relatively good or high quality fits on the inside of this. So when we have large orders of polynomials, we trust what's happening near the middle much more than we trust what's happening on the outside. With that, I want to review what we covered today. We talked about using polynomial coefficients for interpolation. We could get those using linear algebra or Newtonian polynomial interpolation or Lagrangian polynomials. Remember that Newtonians use divided differences. While our Lagrangian polynomial used these L factors times individual f of xi's. We talked about why it's important to use, when we're doing inverse interpolation, to structure it as a root finding problem in order to minimize extraneous oscillations. And then we talked about how extrapolation can be dangerous, as well as how oscillations are going to occur as we get towards the outside of our data set. Okay, see you in class.